Hi, did you know that Visual Studio has some really powerful graph visualization technology? It all starts with the File New menu, where you can create a directed graph. If you don't see the Directed Graph document option, then use the Visual Studio installer to modify the individual components, search for DGML, and make sure that is checked. Directed graph documents are based on a file format called DGML, which stands for Directed Graph Markup Language. DGML is able to represent nodes and links. All right, let's create a node. Foo, and there's a little handy pop-up tooltip here that lets you create links, more nodes, comments, and groups. Let's create another node. Now that we've created this graph, we can save it and take a look at the contents. I'm going to look at it using VS Code, and you'll see several things about this graph. First of all, it contains nodes with the names that we provided. It contains layout information, which means this graph remembers what it looks like. If you save the document in a particular layout, it will remember that layout, but it doesn't have to. So the user can always go here and choose to redo the layout with all these automatic graph layout algorithms, top to bottom. Save that, and now my graph is updated on disk. Nodes and links make up a graph. Nodes can also have properties like this, and it's extensible. You can have any properties you want. Labels, of course, show up on the diagram here. Obviously, this is very general. A directed graph can represent absolutely anything. So what I'm going to do here is I'm going to remove those nodes and just paste in these links. It'll actually create the nodes for me, but this is a graph of links, and I want to see what that looks like, right? So this is the power of visualizing graphs, because I have no idea what that's going to look like. So I'm going to save that and tell Visual Studio to reload. All right, so that's what all those links look like. It's really nice to have this automatic graph layout algorithm built in. It came from Microsoft Research. It's called MSAGL, and you'll find that on GitHub if you want to just use the graph layout engine. And of course, there are different formats, bottom to top, left to right, and so on. Sort of force-directed layout. The top-to-bottom layout is important. It's actually a Sugiyama algorithm that tries to make all these arrows point downwards. So what you end up with is a natural layering of the dependencies in this graph, which can be super useful to find those layerings in your software or any graph. Now, of course, the users can move these nodes around and create a big mess, and they can save that document and it'll remember that mess because it remembers all that bounds information. But any user can come along and use this automatic graph layout to get it all nicely cleaned up again. The main goal of providing automatic graph layout that looks really nice, a lot of work went into making these edges look really nice, is that we don't want people wasting time having to position things all the time. It's just such a waste of effort for humans to be doing manual graph layout when the machine can do, in most cases, can do just fine. You can also add groups to a graph, and here I'm going to take these three nodes, Control-click to multi-select, and I'm going to say put those in a parent group. Okay, so it supports nesting, and I'll call that one whatever. Now if we look at the DGML again behind that, what you'll find out is that a group is nothing but a node with a special property saying that it's a group. In this case, it's also expanded, so it remembers the state of the group. We'll show how collapse works in a second. You can also see that the containment relationship, the nodes that are inside the group, are just represented as links, where the link has a category called contains. This is a special category, and that's how you create a group. So remember, a group could be collapsed, and something interesting happened just here. So there's still links to this thing, right? Those links were automatically computed from what was inside. So what the real links are these ones, and you can see when I select the node, those links are showing up. So this link is the real link in the graph here between A depends on D, D depends on H, but when you collapse the group, A depends on the group, and the group depends on C, right? So what it's done is an automatic summarization up the group hierarchy of the inner dependencies. And this can be a fantastic way to collapse away complexity in any big complex directed graph, but without losing the top level information. A couple more things about the basics of DGML. You can right click and add some sort of tag or category to these nodes. And when you do that, the legend will show you that you're using a category on these nodes. So what we've just done is styled some nodes, and in fact if you look at the DGML, you'll see that those nodes now have a category, and that category has an associated style. In this case, the style is making them green. I could make them dark green, and I could change category 2 to say something green. So now the category is something that I've invented, right? It's not, you can have whatever you want. Let's save that, reload it. Now it says trees, and when you bring up the property window with F4, you'll also see that there. And you can also add categories here. So let's come along and say F has a category of fruit, and I can now go to the legend and say, you know what, I want to style my fruit category with a icon. And so there's this big list of icons you can pick from, and we'll find something that looks fruity and click OK. So now that node has an icon. So a nice little style sheet language to make some lovely looking graphs. What you'll find up on GitHub is a little repo that contains all kinds of DGML demos, which I'm going to run through quickly here just to give you an idea of the breadth of possibilities here. Obviously you can probably already imagine that anything is possible. So let me open up the root demos.dgml that's in that repo. Of course, you can zoom really easily with the mouse wheel. If you ever want to try and remember the keystrokes in the graph, you can always create a new graph and follow these links. So it says quick help for the mouse and for the keyboard. So for the mouse, this graph explains how the mouse works. All right, so a left click can select a node. A left click and a drag will move that node. If you also hold down the shift key, then something interesting happens, which is it becomes a nudge tool. See how it's pushing everything out of the way? It's like a bulldozer. Left click and drag outside a node. If you haven't selected something, it becomes a pan. So if you click on the background, you're going to pan the graph wherever you move the mouse. If you are doing a drag drop operation, you can also drop a selected node. And then if I drag with a shift key down, I end up selecting nodes with a rubber band. And if I right click, drag a rectangle, it will zoom into that rectangle. Okay. If I spin the mouse wheel, it will zoom in and out. If I hold the shift key, it goes left and right. Cool. And then the keyboard help shows a few things. So you can expand and collapse a group with the plus and minus buttons, keys on your keyboard. Star will expand all groups deeply. You can delete nodes with the delete key. You can insert nodes. Let's try insert. And it's wherever the mouse is where it inserts that node, which can be handy, right? I want a node over there, and I want another node over here. That's fine. I can use, all right, F12 will jump to a reference that's stored on the node, and I'll show that in a minute. That's a good way of navigating across multiple graphs. You can ask it to show you the incoming node. If I select this node and type B, it selected the incoming node and the outgoing nodes. If you press I, it does incoming node, and if you're on a node and you press O, it'll select all the outgoing nodes. So that comes a real handy way of expanding a sort of subgraph within a big graph to find directly connected things, and then you can cut and paste them. You can do all kinds of grouping operations on the things that are nearby in a neighborhood. All right, so that's the quick help. That should be a handy way to remember how to use this canvas. All right, back to the demos. What we show here is some different uses of DGML. The first one is going to use some categories, and I'm also going to use the go-to reference. All right, so this graph here is showing a bunch of interfaces, and it's been manually tagged with different icons and different categories. The legend will show us what those categories mean. So we've identified some interfaces that are being obsoleted. We're going to rename some classes. We've also shown in green some external code that we can't change because it's just a dependency. And then, you could have some comments in here. So this comment has a nice little sticky note look and feel to it. This kind of diagram in the past has been super useful to communicate to the team about a big refactoring that was coming up and what's going to change. The next demo is about code coverage. So how can a graph help with code coverage? Well, you can run code coverage on your code base and then color the dependency graph. So this is showing how classes are dependent on each other, but at the same time overlaying that with information about code coverage, where red is bad and green is good and yellow somewhere in between. Notice this legend here shows that there's some kind of funky function going on here. The code coverage is actually computed. The colors are computed in the style sheet for these nodes, which is pretty fun. But the reason why you might want to put that on a dependency graph is you can kind of see hotspots, right? You can see where there's lots of green, right? So that looks good here. I don't need to worry about that. But you can see clusters of red, and you might go over here and go, wow, there's a lot of red in this area. Maybe that's the place we need to focus on for our next testing effort. All right, the next demo is a fun one that shows this sort of icon with a label format with no node boundary. This is actually explaining the dependencies in a game. And the icons are fun because you can now visually see different types of code. You've got networking code, you've got code that deals with data and databases, and you've got UI code, which has a nice little UI icon. So now I can see the different parts of this application and what they're doing. For a really fun one, you can also explore lines of code visually. So here we have scaled the size of the font to match the number of lines of code in a class. So now I can see, if I was brand new to this program, haven't never seen it before, I might start here because it kind of is this center and the biggest guy, so it's probably the most central to the game. And since I wrote this code, that actually is true. All right, now for something completely different. This was generated. This is a graph of all of the dependencies across assemblies. So what assembly depends on what other assembly in .NET 4.0, and of course everything depends on MS Core Lib, right? So that one's at the bottom. As you would expect, the natural layering has been discovered here, and MS Core Lib is at the bottom. Now, of course, the number of links here between these nodes is horrendous, and of course that makes this graph kind of messy. Which brings me to this DGML Power Tool. You can install that into Visual Studio, because it's a Visual Studio extension, and you can see it under here. Alright, so I have that installed, and what that does is it adds two buttons to the toolbar. A neighborhood browse mode and a butterfly mode. So maybe out of all of this .NET graph, I don't care about the entire .NET framework, but I do care about printing because I want to see what all is involved in that assembly and all of its dependencies. I can now select that node and say, show me everything that is one link away from printing and hide everything else. Okay. Now I'm getting a slice through that graph that's much easier to reason about. Now this graph still contains lots of links, as you can see. There's on the legend, you can use the plus button to add an analyzer, and there's a circular reference analyzer. It's actually Tajan's algorithm, strongly coupled components, and it'll highlight in red anything that is a strongly coupled component, so you can see more visually what the circular dependencies are. An architect might come along and go, okay, that's not good, how can we fix that? But this graph is still a bit messy. You can use this other button here, select printing, and go, actually I want to break any circular dependencies, basically turn this graph into a tree. Very nice. Now this type of butterfly mode works really good if you go left to right. Kind of looks like a butterfly, right? I can delete the circular analyzer. Maybe I want to go and be 2 links away now, because the butterfly mode lets me do that. Now the way these buttons work is I can say, okay, printing's good. Now I want to understand the system.drawing and what does he look like. And if you click the neighborhood again with that guy selected, it'll recenter the neighborhood around the selection. Okay, system.drawing obviously is much bigger dependencies. Maybe I want to see this one, and so on. Now I can jump through the graph one node at a time and get the sort of incoming, outgoing dependencies, go back to one link away, system configuration. And now I'm getting to understand the graph, whereas before it was much harder to understand everything all at once. Of course, you can turn off the neighborhood and you can turn off butterfly, and now we're back to the original graph. Now we can add a layer of grouping to this graph to insert some high-level groups that we understand from the code, and this huge mess can be a little bit more reasonable. And let's take a look at that one. So this is the same graph, but now what it's done is it's added a layer of grouping. So for example, we've grouped all of the assemblies that are involved in providing the Windows presentation framework. This graph, of course, makes a lot more sense now. I can totally understand that one. The top level graph also tries to layer these groups a little bit. And then one thing you can do is select all, type minus to collapse all the groups. And now this is the big picture of my groups. Of course, .NET Runtime is still extremely central here. And now one thing that I glossed over a little bit is, remember I said that it only shows all the detail of a link when you select a node. So if I do select all of that mess is what grouping is hiding by default. When I'm deep in the graph here and I do want to understand everything about workflow services, I do need to know what else it's connected to. But of course, I'm so zoomed in now I can't see where they're going, but you can hover over the link and it'll tell you, okay, it's dependent on link from XML. And of course, you can navigate to that assembly. And then that one's now selected, so this process repeats. So I can now jump around this grouped graph, and while it's hiding a lot of detail, that detail is still available to me when I need it. Of course, not all graphs need to be about code. We have some other examples here. This is the Universal Modeling Language meta model, represented as a DGML graph. We have actions, activities, use cases, state machines, and of course we've nicely colored all that with our legend so we can see what's going on. And now you can see that hand-built graphs can be pretty nice to look at. And since all these nodes are colored, I can come in here, select all, right-click, group, remove groups. So remove group is clever. It's able to surgically remove the groups without disturbing the underlying links. So what we get back is a graph that has, if I do a layout now, it's sort of remembered all of the group placements. But if I now do another top to bottom layout, all of those nodes get interleaved in their various top to bottom positions. But the colors still tell you what part of the meta model they belong to. So you can see how interleaved really all these things are, whereas actions, they're pretty much standalone over here, right? So that's interesting to see. Of course, the DGML document supports infinite undo. I can go back all the way back to my grouped graph, no problem. I want to also show that a graph can be used to communicate to a team. I've used this same system to explain how things work. The graph canvas supports drag drop, and so how do we explain that to the user? Well, there's this class, there's comments we can put in here. We can color some things that are really important, and the programmer now who wants to fix a drag drop bug, this is drag drop, right? I can move this node from here to here. And this graph here will explain exactly how that works, including auto scrolling and so on and so forth. Lots of little gesture things and complexities in how does graph layout update and so on, explained visually with these documents. Another one might be how does the layout work, right? So all of these things can explain how the classes work, but the comments also can thread together a story, a slice through the code that explains a particular feature of the overall application. All right, let's look at those bigger graphs. So this is a graph that is big, and this is really here just to show you what the scalability of this canvas looks like. It's all based on WPF, so the scalability is not great, but we've done the best we could do with WPF, which is a lot of virtualization here. So this is actually a virtual canvas, and it's lazily rendering stuff on the fly so you can get something. And this is also a semantic zooming, so there's no detail on those nodes because they're so far away that you can't see the labels anyway, so there's no point creating them. So this is all of the namespaces in WPF with all the classes in those namespaces and the dependencies between those classes. All right, that's a big graph. So over 1,000 nodes and 3,500 links, which means it's a pretty dense dependency graph. Remember the right mouse button trick that I talked about earlier? I can do a right click, drag out the rubber band, and zoom in. Now the labels appear. So that's the semantic zooming I talked about. And you can see that I can still pan around this graph pretty well. It's not great, but good enough that I can still deal with this big graph. Of course, if you've got millions of nodes and millions of links, I wouldn't even try to open it in this editor. For that, we're going to need some other tools. And you can use DGML to kind of represent anything. Recently, I was trying to show a little architecture diagram of how a system worked in building 99 with sensors around the building. There's a server, there's routers, there's Raspberry Pis and Teensies and LED strips, little comments explaining how it all works. And then I can send this picture in email, slapping this together. And then I can just screenshot this and send it to folks. One time I was listening to a Ignite keynote speech by Satya, and I wanted to just actively listen and keep track of all the key points and the relationships between the different things he was talking about, and I find that a useful way to kind of really do some active listening. Another fun use of DGML is a model-based test system that I built for an application. It's a financial application, and I wanted to have a model that explained how the user uses the application, but this model is actually executable. And I can use the bulldoze thing to make some space here. You can see some edge bundling going on there to make these edges route around these tight spaces. All right, very nice. This model is executable. Let me show you what I mean by that. I've installed another extension, which is a DGML test monitor. What this graph shows is that the user can start somewhere and they can create a new database. And when they create a new database, they can either choose a SQL database or a binary XML database. And after that, after the database is loaded, they can populate it with data. They can either add sample data or download the data from a bank. By connecting to a bank, they sign in and so on. This shows you the sort of thought process, the workflow that a user would have to follow if they're editing transactions and so on and so forth. But this represents a model with weights, and those weights determine sort of priorities of how often a user might do these things, so that the test can run all of these steps in whatever's possible according to this graph is what the test can explore. And that way the test won't get it, it's not a total monkey test. It's actually exploring valid scenarios and making sure the test doesn't get stuck in some corner. All right, so with that DGML test monitor, I can open a window called DGML test monitor, and I can dock that over here on the left. And then what I can do is I can execute this test. It's actually a unit test. So, I call it a scenario test because it's really testing the full integration of the app, and I can go ahead and run that. What this test will do, of course, is launch the application. Off screen, it's running the application. I can show you that too in a second, but the application is launched and it's starting to interact. It's selecting categories, right? And you can see on this graph what the test is trying to do. Over here is a log of all of the steps that it has so far performed. And this is a model-based test, so the termination is either it failed to do something, or, which means the app did something unexpected, or it's finished a certain number of steps. I think this test has 500 successful steps through this graph. Then the test will be completed. But what we can see here is that it's running through this model, following the links, exploring the application. Right now it's downloading accounts from a unit test sort of mock bank and testing all of the OFX banking features of the app. Once it's connected to the bank, it will go ahead and sign in. Saving the document, going back to interactive mode, selecting categories and so on and so forth. Selecting payees, going to a currencies view, going back and adding sample data now from the sample database. So now my financial app is populated with data. Once that's done, I can now go and start making reports. Exploring reports, it's going to explore the transactions view here. Zoom out a bit more so we can see the overall graph here. And so this is jumping around, but it's doing things that make sense, right? It's not a complete monkey test. It's a model-driven test. I've found a lot of bugs in the program this way, especially if you let it run a really long time, more than 500 steps. And of course, this is all based on a random seed. So to reproduce a bug, all I have to do is replay that model-based test with the same seed. But this is using the DGML canvas. It's integrated into Visual Studio as well, and it's really fun. I can come in here and add some more nodes, add some more links, put the code behind those nodes and links, and then the model-based test will run and do that new behavior, whatever it is that I've added. I think recently I added the node down here on currencies and for testing the currency view, and that was just, adding a few more nodes. and this can grow and grow as I want to model more different user behaviors. Alright, the test actually failed there, and what you'll see here is that something happened in the test, and I'll get a nice stack trace here saying it was trying to navigate a transfer across 2 accounts and it didn't work. And so now I can look into it and see, is that a product bug? Is it a test bug? I can reproduce it with this model seed. All of this, just to point out that DGML can be used for lots of interesting things. Now, of course, Visual Studio itself has used DGML to do the code mapping feature. So with this solution open, I can right click and say, show me a code map. This is available in the enterprise version of Visual Studio. And what the code map will do is open up the assemblies and then index them in a database, which is what it's doing right now. It's building the code and then indexing the code. What that means is that this graph canvas has the ability to query a database of all the code links, code dependencies, inheritance dependencies, call graph dependencies, everything. And here it says that there's code in this test that uses code in that DLL, and so these links are showing up. I can then so this is a top level view. It's a roll-up view. Basically, imagine find all dependencies. In Visual Studio, you can use find all dependencies at the code level, but imagine doing that for every function. Find all dependencies of every function. That's why indexing that database takes a while. But now I can expand, and it'll instantly, because it has the database, it can now instantly know how all of the namespaces are dependent on each other. I can go one step further and look at the data namespace and drill down into all the data classes. Of course, there being a money application, you can imagine there's payee, there's accounts. Let's take a look at the accounts class. Alright, now I'm down inside a class. I'm looking at methods. So these are method calls. Actually, this is a field read. So these are private fields. So now I can really look at this code and see, okay, there's some key private fields here that lots of things are dependent on. And I can start to reason about, well, if I want to pull this out of this class and move it somewhere else, or this index, what would that impact? And I can look at the incoming dependencies here and get an idea of how much of a tangled web I have in my code and how I might want to fix that. The other thing you can do is right click with the select menu. I can say hide everything that's not selected. Oh, there we go. So that's a fun way to bring the graph down to something reasonable if you get into a big mess. The other fun thing you can do is you can just drag another class onto the canvas. And what this will do is it'll query that database and add any dependent links. In this case, I picked a class that doesn't have anything, but you can get the idea that being able to dynamically build up some things, which works really good if I want to stitch together a story on the graph about how something works. I can use this search thing here. Let's say payee, and now I can add all of these classes onto the graph and stitch together a story about some cross-cutting feature of the application. Drag all that onto the canvas, and then it'll add the dependencies for those things. So pretty rich, powerful way of slicing and dicing code and understanding how it works. One more important feature is that you can also get breakpoints showing up in the debugger on a code map window. Recently I had a bug in this part of the code, and so I put a breakpoint there, run my application, and then when I hit that breakpoint, there's a fun thing you can do, which is you can tell it to show that function on a code map. Alright, and you can also go to the debug window and say show the whole call stack here. So now I can get an idea of how I got to this place. I can run the application again, and every time I get a different call stack, maybe I have to interact with the application, change some things, and I get a different call stack. So now I want to show this call stack on the diagram as well. And I can see some more classes are involved here, and I'm going to ask for the containing types. You can see now how that database has become super useful for slicing and dicing. Now I'm getting a picture of how this property changed event can be interacted with from settings, from the main window, from the changes that happen when a property is changed in the data classes, and I get a better picture of what's happening. So this is code map while debugging. Super useful. You can find more information about DGML, full syntax reference and so forth, up here on learn.microsoft.com.